Okay, so it's good to be back. In the chair, the chair needs to be sitting in the chair. There we go. Cool. Well, okay, so thank you very much indeed, Teresa, for that wonderful talk there. And we are going to now move on to our second presentation. And what we're going to say is Ajayi. Now, she's a PhD student at Loughborough University. Now, I have to say that Loughborough University is one of the hotspots for Black heroes of mathematics. This is our third speaker from Loughborough University. So, you know, it's good to see that Loughborough representing. You probably can tell which university I'm representing today. Right, so, and she is an expert, has an expertise in statistical interference, modeling data analysis using SQL, SPSS, R, and Python. Are you there? Right, okay, this is where I'll talk more. So, there we go. Hello, are you there? Okay, you're muted. Are you there?
I'm here.
And how are you?
Good, thank you.
Yes, I've just been saying that, no pressure, you are from one of the hotspots of the Black heroes of mathematics in the UK, Loughborough University, and I think you're wearing Loughborough University colours, so it's all cool. How's everybody at Loughborough?
Everyone is fine. We say hi.
Cool. All right, the floor is yours.
Thank you, Professor Naira, and hi, everyone. I hope everyone in the room thinks I look like Max, though. So my name is Imoleayomide Ajayi, and I'm a PhD student in mathematics at Loughborough Uni, as Professor Naira has mentioned. Thank you so much for having me today, and special shout out to Professor Naira, who had been a wonderful source of inspiration, especially here in the UK, and also given me the opportunity to present my work with you today. And I'll be sharing part of my research with you. If you permit me a moment to share my screen. Give me a moment, please. So. Okay. Share.
And that's all good. We got modeling low energy electron generation with truncated, normal generalized, linear model, well, that is half your PhD thesis already.
It's just one part of my research I'll be sharing with her today.
Yeah. I hope there's no word count on your PhD. So here we go. Right. So the floor is yours.
Thank you, Professor Naira. So my topic is modeling low energy electron generation with truncated normal generalized linear model. I call it TN-GLM. You're going to be hearing that a lot. Don't worry about the mathematical terms, but I'm going to make it very simple for us to understand. Next. Sorry. Okay. So outline. This is just a little bit of what I'll be talking today through my talk. I'm going to be saying a lot about me and a little bit about micro to nanoplastics, how they're measured, image formation in scanning electron microscope, which is SEM, and the influence of material shape in SEM measurement. So I'll also be talking about the TN-GLM model I've mentioned, and then we'll go to conclusion. So let me take a moment to share with you about a bit about my journey, where I come from, and the experiences that have shaped who I am today. as a Black area of mathematics. So early life and background is on the top left, you see the picture of a little me, which I think is kind of like really, really cheeky. I was born and raised in Nigeria here. And this showed, growing up in a place of rich culture and diversity. I was deeply influenced by the strength and resilience of my family, most especially my mom. My mom has been my great supporter in this journey, and she makes sure that, having lost my dad, she makes sure that I have access to all the things that I needed. And she provided and cared for me, with a hard work. She showed me the importance of hard work, resilience, and compassion. A little, you're going to know more about why I'm talking about this as we go along. But moving on, this was a picture of me at a conference, at a chemistry conference, where we said women are breaking barriers. So I'm saying, as a Black women in STEM and in mathematics are breaking barriers. And you can see from the top right image above, where I've received some awards in Loughborough University. And one of the things I've majorly done in Loughborough is to make sure that I keep appearing everywhere, show my face in conferences, participate, be present. So I think part of what we should do as mathematicians is to be present. This is, my experiences, and I've realized the power of resilience, community, and determination. From my journey from Nigeria to this place, it's been filled with a whole lot of challenges and also triumphs, as you can see in those images. But a little bit about my background and where I fell in love with mathematics. Thank you so much, Teresa, for a wonderful talk, because it is teachers like you who helped my journey and helped me build this resilience towards mathematics. And from this slide, I'm going to share with you how I could have actually, been a dropout at some point and never made it to school, let alone have a PhD. So that's the essence of this particular slide. This is a picture of my primary school on the top left-hand side, where I fell in love with maths. So I had, in this school, I had experience of having a good math teacher and a bad math teacher. So I had a good math teacher up until primary 4 in my primary school. And in primary 4, they brought this teacher from nowhere, and, and he started teaching. In primary 4, my math grades dropped so low, because from nursery school till that time, I was top of my class. But in primary 4, I had a whole lot of struggle because of the teacher that taught it to me. Math is a language, and if it's not taught properly, it would confuse the learner. So moving on to other classes, I began to regain my strength back in mathematics, because I could solve the questions for the year after me in my class. So if I was in primary 4, I could solve primary 5 mathematics. So I was curious, I was inquisitive. I wanted to know how numbers work and all of that. And this school enrolled me for different types of competitions. We will go on competitions, we will come back winning and all of that. And it kept building up my my love for maths. And when I finished in this school, I went to the secondary school, which is, you see, left on the left below the primary school. I went in here on merits, because from my GS1 to GS3, which is the junior class, I performed very well until my grandma was sick and my mother had to use all her resources to cater for her needs and helped her. And, it was a challenging moment for my family. And I had to drop out of this beautiful school here. And the question comes to the mind of a 15-year-old girl who has love for education, love for mathematics, who was doing well in her classes, but there was no funds to further. There was no funds to come back to senior secondary school classes, where you begin to choose your niche or choose whether you wanted to do science or not. So, but my love for education had always spawned from my dad, who was a teacher. And I'd always hold on to that part of him, even though he was late, he wasn't there, but he left that legacy of that education is important. So how I did it was I kept, waiting for my friends to come back from school. I had a childhood friend who would go to school in secondary school, from this same school. And then I would get all our books. I would read when I'm visiting. I would read our physics, our chemistry, our maths textbook. I would practice all of that. And then I practically taught myself secondary school courses, from maths to chemistry to physics and all of that. And when it was time, I enrolled myself into a school, a very local school that, when I mean local, people from Nigeria will understand local school, just to get my name on their school list and, do a school living certificate exams, which I did, and I passed. I sat for that exam once and I passed, having taught myself through secondary school. Okay. And now I've taught myself through secondary school. It was time to go to university. My mates were in university, going to study physics and all other courses, medicine, chemistry, and my family was, still in a state of, the sickness that stopped my grandmom left my family from being, we were not poor, we were middle class, but we went from being middle class to poor quickly because all of that money just went away with our sickness. And then I couldn't go to university. I couldn't afford it. I would ask people for help. They would, as a child, they would want to take me for granted. So, and my faith has always helped me to do things. So I went to this school called Federal School of Statistics, to cut the long story short, and I got admission into the school. And I had a whole lot of, I would say, a whole lot of teachers that were really, really there to support my journey to statistics. It was purely statistical courses that was being taught, and a little bit of computing statistics. This was when I learned SPSS, and even R. So moving on, with the qualification I earned here, the national diploma, I was able to gain admission into a university, finally, a second 200 level in Abeokuta. I got admission to study statistics as well. So now I hold a national diploma in statistics. Also, my BSc was in statistics. So after I finished from Federal University of Abeokuta, I moved on to doing my master's at the University of Ibadan, at the top right hand here, where I also continued in statistics. And all of this, helped me to keep, there was this resilience. I kept pushing. I keep trying to make sure that I gained this education, because education was the only way for me. And if it was the only way, and mathematics was going to be that way, because I've always, loved it. So, and then here I am at the prestigious Loughborough University. Moving on, let me take you through some of the things that really fascinate and inspire the work I do. From education and mathematics to technology and global goals, I find myself constantly exploring how these fields, intersect and how they can contribute to me making a difference, which I want to do. Is math fun? Is math fun? This is like one of my biggest passion, to make mathematics fun and accessible, for young minds. And that's why I've come up with this book, which I'll be, launching very soon. It's just to, you see, based on my experiences, math, I want the world, I want the children, because math is a language. Just like if I all of a sudden speak a different language to my daughter, she would not understand me, at age 5. She wouldn't understand me because she has not been taught how to speak that language. So for me, I want to inspire kids to see math as not something that's intimidating, but as a tool that they can totally use to solve real world problems. So I believe that once kids discover the joy that's in maths, it will open up a new world of possibilities for them. And I want to be part of that discovery. So contrary to what my child's nursery teacher told her when she first come to UK, and she came home and she was like, "Oh, mommy, I want to be a firefighter." I'm like, well, who said that? Because if it's coming from you, oh, you want to be it because you want to be it, is a different thing. But if it's coming from somewhere else, I want to know. So I asked, who told you about firefighters? He was like, oh, my nursery teacher said I could be a firefighter. Which one? I was like, no, it's more like what you want to be, not what your teacher wants you to be. So why is this picture of me and a colleague here? We are just the two Black girls, only Black in mathematics at, doing PhD at Loughborough University. So I thought to put that there to say, to show how unrepresented we are, in mathematics. So which creates curiosity for inclusivity in, in STEM fields, especially mathematics. My interests, I have interest in machine learning. I put this picture there because in Nigeria, prior to my PhD, I was able to use machine learning to fasten loan process and increase profits for the bank as well as make loan accessible to small scale and medium businesses that exist in Nigeria, which is a way of alleviating poverty. So that for me was important. And then the net zero goals is kind of like in alignment with my PhD as well, because what we want to do is combat climate change, and micro to nanoplastics have been found to kind of like contribute to climate change. So I am so intrigued about how technology and maths can be used to contribute to achieving sustainability goals as well, whether through modeling micro to nanoplastic emission, or finding more efficient ways to generate renewable energy. I believe that maths and science can play a critical role in these global objectives. So, and the image of my AI version of childhood is So it's a project I'm currently working on where I'm trying to get children from age 11 to 15-year-old AI ready. So, and I also volunteer as a STEM ambassador and as a woman in data science worldwide. Yeah, enough about me. Let's talk about microplastics. What and why? So imagine you're walking on a beautiful beach and the waves gently lap the shore. But if you look closely at the sand, you will not see with a naked eye the tiny fragments of plastics. These plastics are so small that they are invisible for us to see, but they are everywhere. They are in our oceans, they are in our rivers, they are even in the air that we breathe. So today, we will explore what microplastics are. So microplastics are fragments of plastics less than 5 millimeters in length, plastics particle. We cannot see them. So we need a microscope to see them. So, but nanoplastics are the tiny version of this microplastics because they are less than 100 nanometers in size. Also, they're still invisible to the eyes. So you can practically not see them except you use a microscope. So the problem, the danger to our body is that they are present in air. So when we inhale nanoplastics. They can penetrate your intestinal barrier, causing different types of health issues. And they're also present in the toothpaste that we use. Sorry about that, but it's the truth. And they've been known to penetrate blood-brain barrier, which means they've been found in they've been found in the mice of the brain of mice, and also their research as notes that they also have some contribution to Alzheimer's disease. So these particles, like I explained earlier, are very tiny to the human eyes. How do we see them? How do we measure them? We see them through a microscope. So on the left-hand side is the image of scanning electron microscope. How does it work? It works by shooting a beam of electrons. So instead of light, it makes use of electrons. So it shoots the electrons on the sample, which creates the image of the particle, as you can see in the monitor on the left-hand side as well. But the big problem is with measurement. You might think it sounds simple to use the scanning electron microscope to get an image and measure the particle, but there's a problem. The size that we impute into SEM does not match the measured size. When you take the image and then you analyze it for size, you don't get the same size if you put a particle with a known size into SEM. And size itself varies based on, different settings that exist in SEM. So I'm not going to bore you with the details, but I want to talk a little bit about the image formation in SEM, how this image on this slide is being formed. So SEM uses primary electron beam that hits the surface of the sample, and then it causes interaction to occur. You can see in the shape of a onion, in pink. This interaction occurs here. And that interaction produced different signals. The signals produced could be basketed electron, which means an elastic scattering has occurred. And it will also be low energy electrons, which means another electrons has been produced. The equation for the yield based on theory is yield based on primary electrons that has been showered on the sample, and we will get this as a function of depth. So when I say depth, I mean if you go, as you go down, as the electrons goes down into the sample, that depth of interaction, it is said to influence the yield of low energy electrons, which means the electrons that are low energy that comes out. And these electrons are the electrons that are used to form the image that we saw on the previous slides. Now let's talk about why, sorry, from the previous slide, I mentioned depth, right? That the depth has been said to influence how low energy electrons escape from the sample that is being measured. But it is not just about depth. The shape of the sample that is being measured also matters as well. So why does shape matter? So shape matters because when we use SEM to look at tiny particles, the shape of the sample can change how the electron beam interacts with it. From this image, when you have a flat plane like this, something really flat, this is a flat plane. When you have a flat plane and you shower the beam on that sample, the interaction from the scattering that we have in our plots below each sample, you will see that the interaction is different. When it's a flat plane, the interaction is different, and the red ones are the low energy electrons that escapes from the sample, and the green ones are the ones that ends up being trapped within the sample that is being measured. So when you tilt this plane at 60 degrees, for example, you will see that the interaction is also different. The distance to surface, the distance to the surface where where the low energy electrons will escape from is also different. So shape does influence the way the electron interacts with the sample. And that is why we have come up with a 3D model that takes account for material shape within the sample. I'm not going to bore us with the 3D model, but it's just basically focusing on changing the perception of, say, depth contribute to low energy electron yield to, say, the distance to boundary of any shape, any material shape that is being examined contributes to the amount of low energy electrons that will escape from the sample. Moving on, we have proposed a truncated normal distribution to model the interaction that occurs within the sample, given different shapes and different sample fields when it's been examined with the scanning electron microscope. And this is the result of our model. In this model, we can see that the histogram shows how the truncated normal distribution against other two different distribution fits the density of low energy electrons that are generated within the sample. So the green line is the folded normal distribution, and the blue line is the half normal distribution, while the red line is the truncated normal distribution. And we can see that the red line fits better. And based on the cumulative distribution function on the right-hand side as well, we can see how that curve, fit into the original data. And we didn't stop there. We had to use the goodness of fit statistics, which tells us how each model fits the data. So we usually use the lower number. The lower number means that the model fits better. So for the Kolmogorov-Smirnov statistics, the lower number for this is the truncated normal distribution, and it means that fits a distribution for the plane properly. The same thing for when the plane is tilted. When the plane is tilted, our model also works for the plane. We see that the goodness of fit statistics for truncated normal distribution also fit this distribution for a tilted plane and also for a sphere. So moving on, this shows this slide is really key towards the low electron energy model, TN-GLM. So it shows that at different energy levels, at different primary energy, that our model behaves well for different tilt angles and incident energy, which is the energy at which the electrons first came into the sample. Conclusion. Thank you for listening. We have successfully described with our research the resolution of SEM image, that can be affected by the parameters that are related to sample tilts. And we have also described that the low energy electron generation with a truncated normal distribution as shown in the results we have displayed before. And we propose a 3D statistical model that refines the resolution of SEM. Why is this important? Now, the expected impact is that we can better assess a scale of micro to nanoplastic pollution and its sources. And also, it would help us to minimize generation of plastic waste and aid development of environmentally friendly materials that are less likely to break down into nanoplastics and degrade down into nanoplastics, thereby reducing the emission capacity of micro to nanoplastics in the environment. Thank you very much for listening. My special shout out to Mako Matza and Eugenia Unsika, who has been of immense support supervising my project. And on the right-hand side are the friends I made along the way during my PhD, who we've always kept in touch and, build a community around ourselves. It's really important. Thank you so much for the opportunity to discuss my research, and that'll be all. Over to you, Professor Naira.
Right, well done. This is very, very, very interesting. Now, a lot of people have views on AI and machine learning and data science, especially sometimes, using these empirical methods. But there comes an exception to a rule where it comes to, however, where it's being used in important applications where it's not so easy to find a hidden pattern. So this whole idea that there could be plastic in my toothpaste, I'm telling you, I'm not cleaning my teeth ever again. So I have to say, well, congratulations to you. How far are you into your PhD? Okay.
It's my third year.
How close to the Viva?
Yes, I've done my transfer Viva. So I'm writing up right now. So
Well,
wrapping it up.
we're wrapping up. Well, we wish you all the best with that, and I hope to see you again sometime in Loughborough very, very soon. And but well done. And that's what we have to say. That is the best use. You're doing the best use of AI. This is how you use AI. So we have to say thank you very much indeed. Yeah.
Yeah.